I guess what you want as a geochemist is like a nice straight line trend, and when you don't see it, you can panic a bit, like, oh God, what, is everything wrong? Is there any me?
You're listening to The Cosmic Cast. Hello, and welcome to another episode of The Cosmic Cast. I'm John Fisher, and I'm joined by the usual selection of co-hosts of Marissa Lowe, Elliot Carter, and Ricky Bahir.
Hello.
How's everyone doing? So it's just us this week, isn't it? We just have a bit of a catch up between us, and Elliot, you've got some particularly exciting news because you have a newly minted paper on the market.
I do. Very exciting news.
So
I think I started writing this in 2019, so it's been a while.
Well, yeah. I mean, I guess it's take ages, isn't it, to write papers? So this is just published in GCA, wasn't it? And you just had your proofs a few days ago, did you say?
Yeah, I just got the latest ones today.
Yeah, it's always exciting, isn't it, when you get it all nicely typeset and everything like that.
Yeah, it's really nice to see like a lot of work in a sort of finished form. You can close the book on it.
Yeah. So is this a piece of work that formed part of your thesis then?
Yeah, this paper was the first chapter or the first part of my PhD I did, and the purpose of it really was to look at this really old ophiolite called Leka, try and trace what the origin of the fluids and the history of the fluids that have interacted with this slice of ancient mantle. And I think one of the really cool things was we were able to do that. We were able to show that there's like quite a lot of diversity of fluids in this small patch of a kilometre, a few kilometres squared. We've got most of the diversity that you see globally in halogens is present there from this kind of quite diverse story.
So how do you actually look at something from the mantle?
Yeah, so ophiolites, so I mentioned the Leka Ophiolite. Ophiolites are these sections of oceanic crust and mantle, and they've been tectonically emplaced subaerially. So normally they'd be deep underground, not something you can look at. A lot of what we have to work out about the mantle, we infer from volcanoes and things. Ophiolites are really cool because they've basically something has slid up on top of the continent. So you've got this buoyant continent holding something very dense up in the air. So you can literally go along, look at an outcrop and hammer off a piece of something that was once part of the mantle. And so that's why they're really valuable to geologists. But I guess tied up in that, because they're up in the air, something weird's happened to them. And usually they've been involved in a subduction zone, which is where one tectonic plate goes down beneath the other one back into the mantle. And generally, or a typical way an ophiolite is placed is that a bit sort of slid over the top of that subduction zone and ended up kind of up here. So part of the reason we want to trace this history of different fluids is like, what can we assign to the subduction zone and what can we assign to just normal mantle or altered mantle? Trying to unpiece those two things. In what way is this representative of something really deep in the earth, and what way is it something that's particular because it's had a weird history that's brought it to be sub-area exposed, and we can go and hammer off chunks and whatnot.
So do we know when the Leka Ophiolite was abducted?
Yes, so it was abducted about 500 million years ago. So I think we've got uranium-lead dating on some of the sort of latest melts cross-cutting it. So we think it's about 500 million years old. So it's pretty old as things go.
Yeah. So when you're saying fluids and volatiles, what sort of things were you looking at in particular?
So I suppose fluids and volatiles encompasses everything from like gases to water to potentially CO2. These are all things. What we were particularly looking at is halogens and noble gases. So these are like the last two columns of the periodic table, and they're really good tracers for where has water come from. So if water's interacted with the ophiolite, where did that water ultimately come from? Because and generally we are talking about water here because halogens and noble gases really like to be in water versus in rock or in minerals. They tend to end up in the water, so they're really concentrated there, so they're really good tracers of the movement of water around. So you might have water that's come from sediments, or you might have water that's seawater, or you might have some of these volatiles that are actually part of the original magmatic system, just dissolved magmatic volatiles. And all of those will typically have very different halogen abundance ratios and very different noble gas isotopes. So they're really good tracers for like, where does this stuff come from?
Yeah.
So you make that sound like really simple looking at that. So you just look at a certain ratio and then you can figure out where the water has come from. But I imagine it's not that simple. And what do you actually have to do to get those measurements?
So to get both these measurements, we use noble gas mass spectrometers. So a mass spectrometer is basically an instrument where at one end you ionize something. So you split it into ions, you lose the electrons, and those are accelerated down a flight tube, and they pass through generally some kind of magnet, which will bend them and will separate them out according to their mass. So hence mass spectrometer. So generally something that's heavier basically has more momentum, it has more trouble turning the corner in the magnetic field, so it'll carry a straighter path. And so at the far end of this flight tube, you have a series of detectors potentially, and you detect which of each mass have I got as an electrical signal. So to measure noble gases in that way, fairly simple. We ionize with like a hot filament. The gas goes over the hot filament, ionizes. To measure the halogens, it's slightly more complicated because it's kind of weird, but what we actually do is convert all our halogens, or a proportion of our halogens, to noble gases, and we do that by putting them in a nuclear reactor. So we bombard our samples with neutrons, and this causes nuclear reactions that convert a small proportion of the halogens present in our sample to like proxy isotopes of noble gases. And these, so an isotope is an element, atom of the same element that has a different mass. So for instance, argon, most argon is either 40 or 36 in mass. But from chlorine, we produce this mass 38, which is present in air, but it's very low abundance. And similarly for the other halogens, bromine and iodine, we produce another isotope that's really not very abundant in air. So it's then a very sensitive method, which sort of sounds counterintuitive because there's so many like steps along the way. Like it shouldn't, it doesn't sound like it should work, but yeah, you end up with being able to measure really, really tiny amounts of halogens in really tiny samples. So like 5 milligrams would be a typical amount of sample I'd measure in.
And you're measuring down to like parts per billion level, I guess, in some cases.
Yeah, absolutely. Yeah, you can measure sub-part per billions of iodine.
Which is basically the only way to do it. There's no other method, I think, as far as I'm aware, that you can use to get down to that level.
Yeah, down to that concentration, I think it's the only real method. Yeah. It was mainly developed for meteorites, or I think that was part of the motivation. Is often you have these samples where you really don't have very much stuff at all, so it's great to be able to measure it in a tiny amount. But it's also great for something like what I was working on, because it means, for instance, you can pick individual minerals out and measure those. Now, if you wanted to do some kind of wet chemical analysis, or like XRF, or any of these things you might do in kind of typical geochemistry, you'd need maybe grams of the sample, and to pick out grams of olivine from a partially, from the stuff I was looking at, that would have taken years. But I only had to pick.
So I'm guessing that once you've made these measurements, it's not just a simple story of going, yes, I have this clear signal of this fluid. I'm guessing it's probably a massive mixture of different things.
Yeah. So essentially I plotted, having collected the data, you plot up a point, you're like, oh wow, it's just a huge cloud. So yeah, probably, out of the like 2 years, a lot of it has been just like, why is it so everywhere? And in the end, that became the story. But like, you stare at it, like, I guess what you want as a geochemist is like a nice straight line trend, or that's what you think you want. And when you don't see it, you can panic a bit, like, oh God, what is everything wrong? Is there any me? But I mean, what that's really telling you is that it's complicated and loads of things have happened and there's loads of components.
Yeah.
So how do you start to deconvolute some of that then?
Yeah, with time and effort and maybe some creativity. But yeah, so I guess part of the thing is like our sample set, we had lots of different minerals, different rocks, different rock types they were from, and so kind of, and things of different ages or different osmium ages, and sort of looking at were things different or the same between all those groups, ultimately let you break it down into this story.
I just want to take a jump back. You mentioned that you wanted to look at individual minerals. So how did you take a rock sample and then I take out the individual minerals from it?
Yeah, so what I did is basically just, I had the rock sliced into little thin slices and crushed these up in just a pestle and mortar, like a porcelain pestle and mortar, and sieved them out into different sizes. And generally for each sample or each mineral you were looking for, there'd be a fraction where most of the grains in that were single crystals. So to get, for instance, just olivine, you don't want stuff that's mixtures of multiple grains. Sorry, with dogs making weird noises. But yeah, so and then it's literally just a matter of like staring down the microscope for hours on end. You've got 2 Petri dishes and a very fine pair of tweezers.
Wow. Okay. So you'd actually grab the individual grains with the space.
So most of my stuff I was picking from like less than 0.5 millimeter size. So why it was good that I didn't need grams of the stuff.
I mean, that's crazy because I've seen your hands and they just shake like this constantly.
Yeah.
So you don't know what you got in your sample, is what you're saying.
Yeah. You have to finally balance the amount of coffee you have.
Yeah. And so you were saying, obviously, the story, it seems almost, I'm not having a go at you, it seems almost naive to think that only one fluid process would happen to a sample, especially something that's been, abducted from below, the mantle. So yeah, I don't know, I could be wrong there, but is that the case? Do they often have multiple influences from water over time, or is it not?
Yeah. I mean, I guess you're absolutely right. I guess it would be naive to think you'd only have one. I think what was interesting is that we could kind of, one thing you might think would have a big influence is the sort of the final stage of incorporating this thing into a mountain belt, and that didn't seem to be very important in the story. But before that, it seemed to have phases of high temperature. So yeah, high temperature, what we'd call metasomatism, which is basically adding something to the rock. It's like similar to metamorphism, except you're also adding something, say it's carbon dioxide or water or
something in the fluid realm, basically, the gas or fluid realm.
Yeah, it's a weird word, but yeah, it's basically, fluids, but not alteration. And then alteration, which is where you take your rock and you actually react it with, in this case, water, or it could be carbon dioxide or something.
So when you say, when you say metasomatism is adding a fluid to it, so that could be a gas, for instance. Yeah, but it doesn't necessarily react with the minerals within the rock itself.
No, well, I suppose inherent in it is some kind of reaction.
Okay.
In the idea. But yeah, I mean, you could potentially just add chemical components without changing the mineralogy in any way.
And there's the next step to actual alteration then after that.
Yeah, the two are quite similar in me. I guess alteration is a type of metasomatism. Metasomatism is just
it's a linear scale, isn't it? So because you get 2 types of metasomatism, from what I understand. You get that just alters the chemistry of the minerals, and then it does range into the modal metasomatism, where you then start to change the actual mineralogy of the sample. So it is very much a sliding scale between two M members, if you want. I think they call it cryptic metasomatism when there's no change in mineralogy, if it's just if it's literally just chemical, because it's to look at the rock, it's not obvious that it's metasomatized. You have to look at the chemistry to see that it's not pristine anymore.
Yeah, I guess a classic of that would be sort of peridotites called lertzolites.
Yeah,
people
exactly.
Used to think this is the basic unmelted mantle. This is like original mantle. Yeah, as you melt mantle, you remove all the clinopyroxene, and people used to think it was often thought clinopyroxene in peridotites. Okay, that's completely primary. This just hasn't been melted, but then people showed that often that stuff is actually introduced by other melts later on.
Yeah.
So that's like a classic example of metasomatism.
Yeah.
And kind of cryptic,
Yeah.
often.
Yeah. Yeah.
You kind of reproduce back to what could have been an original rock without some process, but that process and its opposite.
Yeah. Which I guess shows why looking at the chemistry of these rocks are so important, because you can't necessarily tell just by looking at something. You do need to take a deeper dive sometimes.
Yeah, and really looking on like the mineral scale as well.
Yeah,
like I think
exactly. Bulk could be hard to tell sometimes.
Yeah, so I think in the paper, I think we pull out like 4 or 5 fluid end members at least, and I don't think you'd have seen any of them really from just bulk rock measurements. You'd have hardly, it was only when you got down to measuring fresh olivine, you could see the high temperature stuff. So the olivine's the primary mineralogy. You can see this high temperature fluids come through. It's really extremely enriched in iodine. So it looks like that's kind of classic of a subduction zone signature. That's the only places that's been observed anywhere else in other places. So you have some kind of subduction signature seems to be the very first thing you have in these rocks, which is interesting in itself because a lot of people have talked about them like they're basically just ocean floor. They're a simple place where you can study ocean floor processes, and you can study those, but the whole thing has to be happening in a subduction zone setting, and that definitely complicates the interpretation of the whole thing.
So that's what you mean, that very few of the actual influential processes were when it became a mountain range. Most of them are actually in that pocket, whereas in a subduction zone setting then.
Yes, that's
okay.
That's what it seems to be. And interestingly, within that, you have a lot of variation. So you kind of it's almost bookended. So we know it happened. There's a subduction zone signature as the first thing, and we know eventually it was in a mountain range. But between those, there still seems to be an awful lot of diversity and multiple generations of serpentinization and different. The serpentinization is when peridotites, that's what makes up the mantle, reacts with water, and that seems to have happened multiple times, which is interesting because people, tend to think, this is a seafloor serpentinite, this is a subduction zone serpentinite, and here you're kind of in a subduction zone or somewhere proximal, and you're getting all of them. You're getting seafloor like ones, you're getting subduction zone like ones. Startling diversity in just a very small area. You can track that even though it's 500 million years old.
So I guess because there's such diversity on such a small sort of geographical scale, I guess that must tell you something about the scale of some of these processes. They must be highly localized then, or is it just stuff that's sort of not being overprinted fully? Or I mean, how does that sort of?
Yeah, I would probably guess it's more like multiple mutually overprinting things, but that aren't completely overprinting.
Yeah.
And that is what we ended up saying in the paper, is essentially we can track here as a temporal shift in the fluid composition.
Yeah. So if I sort of, to give an analogy then, is this right? So basically, would this be equivalent of, say, you've got like a big blank canvas and a paintball gun, and you're like shooting different colored paintballs at a blank canvas, and your job as a geochemist is trying to unpick all the different layers effectively? Is that kind of
that's about right, actually. Yeah, that's definitely, that's pretty close to what the final synthesis picture looks like.
And in that hypothetical scenario there, do you have a time scale between each paintball hitting the canvas, or do you not know? Is there not a way of measuring that?
No, we don't really have that. It's just, I don't think there's nothing that would really date serpentinization that precisely. It's more like a relative petrological, or sort of a timescale based in events you can see that happened in the rocks, but not one that's got anything tying it more broadly.
Well, that's really-
Sorry, go on, John.
No, go on.
In a more broad scale, though, is there a way of timing when it was in a subduction zone to when it has now been abducted? Or is that also not possible?
I guess the two, I think, in geological terms are thought to be almost indistinguishable.
Oh, wow. Okay, so a fairly quick process then. Oh,
I think so, yeah. I mean, again, we're drifting outside of what I know. We're now
yes, yeah.
like tectonics and geodynamic people. I'm sure they'd have things they knew about that. Yeah, I don't know, but I think it's fairly quick. I mean, broadly, like when it abducted is relatively unconstrained. So the date of the ophiolite comes from like a felsic or a like quite evolved dike that cuts the upper part of the ophiolite.
Right, okay.
Yeah, so exactly how close that is to when it was on land is
Yes,
clear, but it's around then. Yeah.
Basically, the paper is saying it's not that simple, really, to be able to go, it's just this one thing happened to it. It's obviously, multiple things happen to an ophiolite as it's, being abducted and etc. But it seems like your interesting conclusion is that most of it happens when it's in the subduction zone.
Yeah.
So was this the first time that sort of high resolution halogen data has been analysed from these sort of samples? Or
I mean, Mark Hendrick's probably done similar stuff, but maybe a bit less like mineral based.
Well, it sounds like a really complicated story then, Elliot, and you've done a really good job trying to untangle some of this then by the sounds of it. I guess we'd probably better wrap up for the week now, unfortunately. Ricky apparently has other things to do with his life this afternoon. But quite, yeah. But anyway, so this article is online, and there'll be a link in the episode description. And if any of you lovely lot wishes to read a bit more about this ophiolite, hopefully the proofs should be up, I guess, by the time this episode goes live. If not, just the unproofed PDF version is available. But yeah, so Elliot, thanks for chatting through that. That was really cool. Yeah, congratulations. And there we go. So I hope you enjoyed this episode, and well, we'll see you all next week for some more Cosmic Cast fun times.
Bye.
Bye.
Goodbye.